Namaste. Today we are presenting on the third chapter of Idols of the Mind versus True Reality, the book by our serving director, Sripad Bhaktimadhava Puri Maharaj. This title is called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So anyone who watches this and who is interested in learning more about the book or the Bhaktivedanta Institute can reach out to us at Princeton at bviscs.org, as you see here. And here is our serving director. So this chapter starts by introducing us to the identity of indiscernibles. The identity of indiscernibles is a principle of analytic ontology first explicitly formulated by Wilhelm Gottfried Leibniz in his Discourse on Metaphysics, section 9. It states that no two distinct things exactly resemble each other. This is often referred to as Leibniz's laws, Leibniz law, and is typically understood to mean that no two objects have exactly the same properties. So we'll see an example of this later on, but now this idea is being explained further, or the context for this idea and its applicability to mathematics in nature the context is being developed here by a quote from Eugene Wigner. We'll describe who he is a little later. This is from an essay that he wrote titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences, just like the chapter of this book. Chapter 3. So Eugene Wigner says that I would say that mathematics is the science of skillful operations with concepts and rules invented just for this purpose. The principal emphasis is on the invention of concepts. Mathematics would soon run out of interesting theorems if these had to be formulated in terms of the concepts which already appear in the axioms. Furthermore, whereas it is unquestionably true that the concepts of elementary mathematics, and particularly elementary geometry, were formulated to describe entities which are directly suggested by the actual world, the same does not seem to be true of the more advanced concepts, in particular the concepts which play such an important role in physics. Most more advanced mathematical concepts, such as complex numbers, algebras, linear operators, Borel sets, and this list could be continued almost indefinitely, were so devised that they are apt subjects on which the mathematician can demonstrate his ingenuity and sense of formal beauty. In fact, the definition of these concepts, with a realization that interesting and ingenious considerations could be applied to them, is the first demonstration of the ingeniousness of the mathematician who defines them. The depth of thought which goes into the formulation of the mathematical concepts is later justified by the skill with which these concepts are used. The free electron theory raises doubts as to how much we should trust numerical agreement between theory and experiment as evidence for the correctness of the theory. We are used to such doubts. A much more difficult and confusing situation would arise if we could someday establish a theory of the phenomena of consciousness or of biology, which would be as coherent and convincing as our present theories of the inanimate world. Such a situation would put a heavy strain on our faith in our theories and on our belief in the reality of the concepts which we form. It would give us a deep sense of frustration in our own search for what I called the ultimate truth. The reason that such a situation is conceivable is that fundamentally, we do not know why our theories work so well. Hence, their accuracy may not prove their truth and consistency. Indeed, it is this writer's belief that something rather akin to the situation which was described above exists if the present laws of heredity and of physics are confronted. So, as I said before, Eugene Wigner wrote this essay with the same title. So the title of this chapter is based off of this essay, actually. He is a Hungarian theoretical physicist and won a Nobel Prize in physics in 1963. He won his prize for contributions to the theory of the atomic nucleus and elementary particles. So he is a well-established and respectable and widely accepted physicist. So he knows well of the role that mathematics has played in the explanation of nature and what is the truth of that role. So he's explaining here that when they are describing non-living, he said inanimate, when they're describing inanimate mechanical phenomena in nature, then mathematics is helpful, and we don't doubt that. But nature is not limited to inanimate objects. Right? Nature isn't just filled with rocks. Nature is filled with living conscious entities. And living conscious entities, they demonstrate behavior and they engage in activities which are beyond the scope of mechanical logic, as we explained in our previous 2 presentations ago on the logic of life, chapter 1 of this book, Idols of the Mind versus True Reality by Sripad Bhaktimadhava Puri Maharaj. So here Eugene Wigner is pointing out that as far as mathematics actually applies to a living reality, that has not been proven, and that mathematics is genuinely more of a demonstration of the complex ways with which mathematicians can explain something. It's a demonstration of what they think is intelligence. It's a demonstration of a complex explanation, but there is no the correlation of that explanation to the true phenomena, living conscious entities in nature. That is not there. And he is pointing this out in this quote. Let's go back. He specifically says that the emphasis of math is on the invention of concepts. So if we're trying to understand the truth of nature, we cannot be worried about inventing concepts. We should be worried about understanding what is already there. So this difference is important. The point is that counting numbers in mathematics and counting physical objects deal with different entities. So Sripad Bhaktimadhava Puri Maharaj is pointing out something very important here, which we can see very easily, actually. These 3 apples, they're not identical to each other. Each individual contains unique qualities such as shape, weight, etc. Strictly speaking, 3 indicates 3 instances of a single identity. We uncritically will say, 3 apples, but these are not 3 instances of the same thing. We can see just by the shape. These apples have different shape, what to speak of their weight, color, and other characteristics. So mathematics actually only applies to abstract mechanical thinking. It doesn't actually truly apply to manifest entities outside of our mind, because there is, like the identity of indiscernibles says, there are no 2 objects which are exactly the same. So how can you say 1 + 1 = 2? It is not 1 and 1, it is just two different things altogether. So the next section of this chapter is called Galileo's Error of Primary and Secondary Properties. Galilei, from 1564 to 1642 is when Galileo was alive. He proposed that mathematics was the language of the book of nature, innovating the use of mathematics in what has become modern science. What is usually not explained is that Galileo had a particular view of reality that made this seem possible. Primary properties were quantitative, such as size, weight, and so on. Secondary properties were qualitative phenomena, such as taste, color, and so on. These secondary qualities belonged to the sensory organs perceiving physical objects, but not to the objects themselves, which possessed only primary properties. Thus, color, for example, was determined by the sense organs of human being or other creature, and not by the object being perceived. So these are quotes from the book. And we'll see how this relates to the rise of mathematics being applied and claimed as a sufficient explanation of how nature works, the underlying mechanics of nature. So based on Galileo's description, primary qualities are qualities which they exist in the apple despite how we perceive the apple. So those primary qualities which exist in the apple despite our perception of it are only about its extended spatial nature. So it has a weight, it has a measurable dimension, and that's it. That's what Galileo says primary qualities are. The secondary qualities are more qualitative in nature, not so quantitative as the primary qualities. So these secondary qualities are texture, what we feel, what we see, what we hear, what we smell, what we taste. These are known as secondary qualities. So when we see their apple being red, this is known as a secondary quality, and Galileo says this is happening either, there's two different interpretations essentially of what Galileo was saying. Either it is happening in our consciousness, the apple being red, or tasting sweet, or feeling hard, or appearing shiny. It's either happening in our consciousness, subjectively, or it's happening within the sense organs individually, meaning that the shininess or the redness of the apple is perceived by the eye, just by the organ, by the eye, or the sweetness is perceived by just the mouth, or the hardness by just the sense of touch in the hand. But that's not such a comprehensive explanation because it's abstract in that sense organs, the body parts, don't perceive anything without a living conscious entity in the body, right? A dead body, an inanimate corpse. The eye is there, the mouth is there, the hands are there, but seeing isn't there, tasting isn't there, and feeling isn't there. You need to have a living conscious entity animating that body in order to experience these things. Simultaneously, it's not just subjective. It's not just happening in the consciousness. There is something outside which is being, something other than the consciousness which is being perceived. So it's a relation. There's a relationship between subject and object. And this applies to both the subject behind the body and the relation between the subject and the external object, such as an apple. So a more holistic and comprehensive vision may be necessary when considering these things. A more integral metaphysics is needed to heal the division that was promoted by Galileo and others. The mathematization of physical nature was based on a metaphysics that is divisive and incomplete. And so that divisiveness and incompleteness will make more sense in our conclusion later on. But first, we're now going into the next section of the chapter, the philosophical development of ideas that science ignores, which led to this idea that math explains fundamental nature. So we just talked about Galileo, who essentially proposed that mathematics was the language of the book of nature. Then, within the same time period, Descartes was there, and he also held the idea that math applied to nature, and he forged the idea of numerical nature of space and time specifically. Then a little bit later on, but still overlapping with Galileo and Descartes, was John Locke, who argued that extended objects were distinguished from extended space. Then we have George Berkeley, who explained that primary qualities are determined by experience as much as secondary qualities. He tried to bring the idea of the objective world into the subjective mind. Then we have Kant, who tried to reinstate the denuded objectivity of the things in terms of an abstract thing in itself, the noumenal, that was unknown and unknowable, but logically posited by thought. Then we have Schelling, who furthered this holistic development in philosophy by offering that the subjective and objective worlds were perspectives that were identical in their difference, thus overcoming the strict divide between them. Finally, we have Hegel, who brought the whole development to an absolute conclusion by explaining that the idea of the world was not in a particular subjective mind alone, but that there was also the idea of the objective world within which the particular observer is included. This leads to the necessity of a comprehensive absolute idea that has being in and for itself, in which both the particular subjective and universal objective perspectives are dynamic participants of a higher unity and difference that preserves yet sublates them in a negative, self-conscious individual entity. So Hegel's conception not only is harmonious as far as the relationship between the apple and object and the subject who knows the apple, but also about the objective reality in which that relation is occurring. So not only is there a relationship between the apple and the thinker, but also between the thinker and the entire environment in which it's participating, which allows it to think, be alive, be conscious. What is that absolute context within which this dynamic activity is happening? And that is what Hegel articulates in a very rational, step-by-step and beautifully comprehensive way. So from Panto Crater to chaos. Now, we just established this succession of thought that started with Galileo and throughout time ended with Hegel and what we presented here. That shows a shift from this purely external consciousness where we don't even consider consciousness itself as a primary fundamental aspect of reality. We're just purely absorbed in the external objects and relations of external objects in a mechanical way. And the development of how that mechanical interaction is just a small, very small part in a wider perspective of dynamic relations between subjects and objects in various scales and in dynamic ways. So now we're going to show that Newton himself, who is a father of modern science, one of the founding fathers of modern science, specifically mechanical worldview, but that Newton's conception of the mechanical nature of things was not isolated as it's presented today. Newton his conception of mechanical operations was within a context where God was necessary, as we'll see what's written here. So Newton had to invoke a Panto Crater to correct for the unavoidable disastrous perturbations that the planets in the solar system would suffer in their journeys. We went over this more in depth in the second chapter of the book in the presentation that we gave. The second chapter is called Idols of the Mind versus True Reality, and we'll put a link to that so you can see the more elaborate explanation of what's going on here. This is one quote from that second chapter. The mathematical bones of Newton's Principia Mathematica were taken by modern physics and presented as a mechanical model of the universe without the Panto Crater. Of course, Newton himself wrote his mathematical section as a whole, surreptitiously, including his remarks about Panto Crater only in an appendix or a scholium. However, the fact remains that observations of the solar system's movements were used to validate both Newton's and modern non-deistic theories, although they referred to very different imagined realities. So the short version of what Newton was presenting was that he was looking at a whole, reality as a whole, living conscious whole, in which the existence of God, what he called Panto Crater, the supreme controller, was necessary. Otherwise, there would be such disaster in the solar system from planets colliding and so many dynamic factors in the solar system that the probability of things just crashing into each other is much higher when we're thinking that it's just mechanical laws. So in order for those things to be organized and moving in a very nice, methodical, neat way requires necessarily some intelligence which is organizing. When there is no intelligence, that's when chaos arises. That's when there's crashes and all these bad things happen. But when there's an organizing intelligence, it's neat. Things are happening systematically, but it's happening in a harmonious way because intelligence is there. And intelligence means a thinker is a personal entity. It's not some impersonal thing. So the problems created by mathematical mechanistic theories in cosmology have led to a crisis in the deterministic model that has ruled scientific thinking in the modern period. It has given rise to the theory of chaos that is now the reigning concept of the universe, which cannot simply be swept under the carpet by those who still support the doctrine of mechanistic science. In 1986, James Lighthill said in a speech that we are all deeply conscious today that the enthusiasm of our forebears for the marvelous achievements of Newtonian mechanics led them to make generalizations in this area of predictability, which indeed we may have generally tended to believe before 1960, but which we now recognize were false. We collectively wish to apologize for having misled the general educated public by spreading ideas about the determinism of systems satisfying Newton's laws of motion that after 1960 were proved incorrect. So Sir James Lighthill, who is humbly and honestly admitting this, he is to be taken seriously. He is a British mathematician who was considered one of the greatest mathematicians of the 20th century. His innovative contributions to such fields as applied mathematics, aerodynamics, astrophysics, and fluid mechanics found in applications such as the design of supersonic Concorde jetliner and noise reduction in jet engines. So he is a legitimate mathematician who has helped the productivity of the world. And he is saying like this. He is admitting that the mechanical metaphor being applied to nature is not correct. Yet it is still something that modern science generally and the masses hold on to. And it causes a lot of problems, as we'll explore in another presentation. So everyone who is seriously, so this is the next section of the book, Logic of Mathematics Compared to the Logic of Nature. Everyone who is seriously involved in the pursuit of science becomes convinced that a spirit is manifest in the laws of the universe, a spirit vastly superior to that of man, and one in the face of which, with our modest powers, we must feel humble. This is something Einstein said. And here's another quote by Einstein. One reason why mathematics enjoys special esteem above all other sciences is that its laws are absolutely certain and indisputable, while those of all other sciences are to some extent debatable and in constant danger of being overthrown by newly discovered facts. It is mathematics which affords the exact natural sciences a certain measure of security, to which without mathematics they could not attain. At this point, an enigma presents itself, which in all ages has agitated inquiring minds. How can it be that mathematics, a product of human thought which is independent of experience, is so admirably appropriate to the objects of reality? Is human reason then, without experience, merely by taking thought, able to fathom the properties of real things? In my opinion, the answer to this question is briefly this. As far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. Thus, the employment of mathematics in science is more or less just to give the scientists comfort and security rather than any real or ontological connection between mathematics and science. Furthermore, Gödel did much to dispel even the certainty that mathematics falsely claimed for itself. This is referring to Gödel's incompleteness theorems. So our conclusion is that modern science uncritically presupposes that noumenal reality, reality in itself, contains extended spatial dimension as a fundamental property, as opposed to recognizing spatial dimension as a description of reality derived from the phenomenal perception of our limited perspective, which implies the fundamental role consciousness and its higher development. This uncritical presupposition has given rise to the largely unquestioned acceptance of modern mechanistic science. Within the mechanistic view of reality, mathematics appears to be directly related to the underlying operation of mechanical nature. However, when we realize that the machine metaphor for nature is overly simplistic and that it is not comprehensive enough to adequately explain all of the observed dynamic activity of living conscious entities, then we also realize the limited applicability of mathematics to nature. So, this, again, is the third chapter of Idols of the Mind versus True Reality by the serving director of the Bhaktivedanta Institute in Princeton, New Jersey. The author is Shripad Bhakti Madhava Puri Maharaj. We will continue with the last two chapters of this book, and we hope that this can generate some dialogue. If you're interested in discussing this, please send us an email at princeton@bviscs.org. Namaste.